time to learn a little bit about statistics. First of all, statistics is the science of collecting, organizing, analyzing, and interpreting data in order to make decisions. When we use the word data, we mean information that comes from observations, counts, measurements, or responses. Here's a couple of random statistical facts like those you might encounter every day. 31% of American adults find giving up their smartphone for a day more difficult than giving up their significant other. 49% of Americans cite a lot of stress at age 22, compared with 45% at 42 and 20% at 70. I'm going to introduce a couple more terms and then we're going to go back to those statistics. So, when we use the word parameter, that's a numerical description of a population characteristic, whereas a statistic is a numerical description of a sample characteristic. A population must include everyone, whereas a sample just selects a few individuals to include. So if we say that in this survey of several hundred American adults that we found 31% have a difficult time giving up their smartphone, since the 31% was based on a survey of hundreds of American adults, and that's only a portion of the entire American adult population, that would be called a statistic. If the survey had been given to all American adults, which is highly unlikely because it's difficult to do, the 31% in that case would be called a parameter. Now, statistics can be used to help clarify things, and they can also be used to manipulate. We live in a data-driven world. Statistics can be used to present that data in a meaningful way, and when properly collected, analyzed, and displayed, data can help us gain new understanding. But they can also be used to manipulate, mislead, distort, or downright lie. Knowing what can go wrong helps us to become sensitive to potential defects in presentations or interpretations of data. We're going to take a look at several problems that can occur accidentally or deliberately. So, descriptive statistics is the branch of statistics that involves the organization, summarization, and display of the data. So let's look at some visual displays of data. The first is a case of TERRI. She suffered brain damage in 1990, which left her in a persistent vegetative state, which basically means there was no brain activity. In 1998, her husband decided to have her feeding tube removed. Her parents opposed the decision, took the issue to court. In 2005, the courts ruled that the feeding tube should be removed. President George Bush signed legislation designed to keep her alive. This case drew media attention by pro-life groups and disabilities rights groups. So what's wrong here? Here you see a graph, and this was posted by CNN, and it looks at how members of various political parties felt about this court's decision to have the feeding tube removed. And when you first look at this graph, you can see Democrats, this huge bar labeled 62, that they agreed with the court's decision to remove the feeding tube. And notice the amount of Republicans and independents seems significantly smaller. But what's wrong with that? Well, the difference in percentage points between Democrats and Republicans is 8%, and the margin of error is 7%. It's likely that the difference is actually less than what is pictured. The graph also does not accurately display that a majority of all groups interviewed agreed with the decision. This is what the graph should have looked like. Notice now the bar for the Democrats does not seem to tower over Republicans and independents. The difference here is that the scale on a graph must always start at 0. If you don't start it at 0, you can distort the differences. Now, there's an 8% difference between 62 and 54. With a 7% margin of error, that means this 62 could actually be up to 7 points lower. So, in fact, it might represent 55%. In that case, Democrats, Republicans, and independents are nearly equal. Graphs can be used to make it look like there's disagreement when there's actually more agreement. What's wrong with this graph? If you look carefully here, we've got Steve Jobs down in the corner. This is a graph from an Apple presentation. And if you look at it closely, you see this green pie section is labeled 19.5%, which is Apple. And the purple section is labeled 21.2% and is in the back. Now, to most people, the green section would actually look bigger than the purple section, but the percentages tell a different story. When you have a tilted pie graph like this, areas in the front usually look bigger to our eyes than those in the back. So this graph kind of misleads and makes it seem like Apple is in second place in the smartphone market share, when actually it's in third. Who's presenting this data? And why would this visual be preferred? Was this intentional? I think you can make a case either way. Now, problems can also arise, not just in the display of data, but what we infer from it. This is called inferential statistics. This is the branch of statistics that involves using a sample to draw conclusions about a whole population. Here's a graph that could be used to make the case that global warming isn't real. You can see this graph shows a trend line in the global air temperature, and notice when you connect the first data point to the last, the trend is downward. So someone who wanted to make the case that global warming is not real might use this display and allow people to infer, looks like it's trending down. However, here's what the graph looks like for the portion of time from 1980 to 2012. And if you go back even further, here's what the graph looks like from 1900 to 2012. So notice how, in fact, steep the trend has been. By choosing a certain graphic over another, there's the ability to manipulate what people interpret. The population, as we said before, refers to the collection of all outcomes, responses, measurements, or counts that are of interest. The sample is just a portion of that. Now, for reasons that are probably obvious, a lot of times it's hard to survey an entire population, which is why we rely on samples. What can go wrong with data sampling? Here's a case that involved the magazine Literary Digest. They conducted a poll to predict the winner of the 1936 presidential election, which was between FDR and Alfred Landon. Previously, they correctly predicted the outcome of the last 5 elections, often within a percentage or two of the actual votes. So they were considered a reliable source when it came to trying to predict or infer what was going to happen in the election. They sent out 10 million surveys and they got 2.4 million responses, which is a decent response rate, sadly. Their results showed that Landon was going to win over Roosevelt in a landslide. The actual election results were much different. Why? Because in 1936, it was the middle of the Great Depression. The people that they chose to sample came from magazine subscribers, telephone directories, and car registration records. If it's the middle of a depression, subscribing to a magazine or owning a telephone or owning a car were luxuries. So the population they sampled for this survey was a bad sample because it didn't represent the whole voting population. It tended to only represent the wealthier portion. George Gallup saw the flaws in this poll and did his own survey. Gallup took random samples of their data and correctly predicted what the magazine's prediction would be within 1 percentage point. Gallup's accurate prediction of the coming era by Literary Digest gave him a lot of credibility and made him a leader in the polling industry. So if you ever heard of Gallup polls, this is the gentleman who founded it. Now, problems can also arise in the analysis. Take this headline: over 2 million Americans exposed to drinking water will die this year. Is it true to say that the people who've died probably have been exposed to drinking water? Sure. But this headline seems to imply that perhaps the drinking water caused those deaths. And that's a leap. You cannot assume that just because the 2 million Americans drank water and they had that in common, that that was the cause of death. So beware of those overly dramatic headlines. And just because two things occur at the same time doesn't mean that one caused the other. And as one last example, take a look at this Rasmussen poll that asked, did scientists falsify research to support their own theories on global warming? 59% somewhat likely, 35% very likely, 26% not very likely. Look closely at those percentages. You should notice that the percentages add up to more than 100%, which shouldn't be possible. In this case, when they tallied their data, they counted some of the very likely voters with the somewhat likely voters, essentially counting people twice. And that's the reason the percentages are off. So I hope that this presentation has given you some basic definitions, which are important, but also has gotten you thinking about how you have to be critical when you read or confront any sort of statistics.